This video is a basic introduction to the scientific notation known as powers of 10. And just like to start with some numerical examples here. So 10 can be written as 10 to the first power, or 1 times 10 to the first power. 100, well, that's 10 times 10. There are two factors of 10. And we write that as 10 to the second power, or 1 times 10 to the second power. 10 to the first power, 10 to the first power here. You can always multiply something by 1 and not change the value. 1,000, 10 times 10, that would be 100. Times 10, that would be 1,000. That's represented by 10 to the third. Or if we multiply that by 1, 1 times 10 to the third. So we have this exponent of the base 10, 10 to the first, 10 to the second, 10 to the third. That's really telling us how many factors of 10 have been multiplied together to produce the number. So that's the key in this powers of 10 notation. It's how many factors of 10 that we have to produce the number, or how many places we shift the decimal. So this 1,000, if I put a decimal point here in that location, if I would shift 3 places, 1, 2, 3, that would bring me to 1.000 times 10 to the third. And I'm not keeping track of significant figures as I do this video. So 1 times 10 to the third. So some other examples here with numeric names. 1,000, 1,000, we've seen that up above. That's 1 times 10 to the third. If we go to 1,000,000, that's 3 more zeros here. Well, 3 more zeros, you can see the pattern. There are 6 zeros to the right of this 1. If I would move the decimal to this location from here, that requires 1, 2, 3, 4, 5, 6 shifts. And we have 1 times 10 to the 6. 1 billion, that's 3 more zeros. The power of 10 goes up by 3 more. I would ask you right now, how many factors of 10 are there in 1 billion? 10 times 10 times 10, how long does that go on to create 1 billion? Well, you can get your clue back here if you remember. The power of 10 is how many factors of 10 are involved. So there are 9 multiplications of 10 on itself to produce 1 billion. 1 trillion, 3 more zeros, that's 10 to the 12th. Okay, that's all with a 1 involved out in front of the power of 10. What about if we have a number? So let's say 500,000. How do we work that into this scheme of powers of 10? Well, 500,000, that's 5 times 100,000. If I factor that out just a little bit, 5 times 100,000. Well, this 100,000, that's 100 times 1,000. So 5 times 100 times 1,000 is where we are right now. We can recognize that 100 is 10 times 10. 1,000 is 10 times 10 times 10. How many factors of 10 are involved in the multiplication? 5 of them. So our result would be 5 times 10 to the 5th. That would be our scientific notation to represent this large number of 500,000. And the scientific notation is valuable, keeps us from making mistakes as readily as if we would just write out this long number and try to keep track of all the zeros that we've written, that we should be writing down. So large numbers, also small numbers, we'll see in this next little example, benefit by using scientific notation. So let's try a different number here. 3,780,000. 3,780,000. Well, if I want to account for the zeros after the 8 here, I could do 378 times 10. That would deliver to me the 3780. And then we have 3 zeros here, so I'll multiply by 1,000. 10 and 1,000. This is 10 to the first, this is 10 to the third. Multiplying together, that creates 10 to the fourth. And 378 times 10 to the fourth. But that's not in the traditional scientific notation. Often we just want one digit to the left of the decimal point. So we don't want 378.0 or whatever, 378 point times 10 to the fourth. Instead, we want to have 3.78 and some appropriate power of 10. So let's examine how we can modify 378. Is 378 the same value as 37.8 times 10? Yes. Is 378 equal to 3.78 times 10 times 10? 100. Yes. Is 3,780,000 equal to 3.78 times 10 to the sixth? Yes. And if you just back up to here, I had 10 to the fourth. I've gone to 3.78 and two more factors of 10. So two more factors of 10, we go from a 4 to a 6 on the number here, or if you want to move the decimal place, if your decimal place is here with the original number, 1, 2, 3, 4, 5, 6, 3.78 times 10 to the 6. Now some small numbers. So if you're talking about light in astronomy or physics, and you want to use standard metric units of meters, then you have some difficulty here. Again, doing this repeatedly and not making an error in how many zeros you're writing down. But it does turn out that blue light is about this number, 0.0000004 meters. And if you do this as your career, you're going to, or as a student, when you're in that topic, writing these small numbers, tedious, and you might leave off one of these zeros or put one too many in. As you key this into a calculator, could be a problem. So we have an example here. So I'll get back to this number, but let's take a look at 0.8. Would you say that 0.8 has the same numeric value as 8 divided by 10? Yes. 0.8 equal to 8 times 10 to the first power? Yes. I'm just rewriting 10 as 10 to the first power, only one factor of 10. Is 0.8 equal to 8 times 10 to the minus 1? Though there's a rule for exponents, when we divide, we bring this base up to the numerator and reverse the sign of the exponent. So 10 to the plus 1 in the denominator becomes 10 to the minus 1 in the numerator. Okay, so review the laws of exponents in a math book if you need help with that. Let's take a look at another example. So 0.08, that's 8 divided by 100, 8 hundredths. This is 8 tenths. This one's 8 hundredths, 8 divided by 100. 0.08, is it the same as 8 divided by 10 to the second power? Well, 10 to the second power is 100, so yes, that's true. Is 0.08 equal to 8 times 10 to the minus 2? How did this minus 2 result? Well, we had 10 to the plus 2 in the denominator. If I want to bring this exponent up to the numerator, I reverse the sign of the exponent, so we get 10 to the minus 2. And something, just a quick check, if you are writing numbers that are smaller than 1, writing them in scientific notation, powers of 10 notation, make sure you come up with a negative for any number that's smaller than 1. So 0.08, 8 times 10 to the minus 2. And the reverse is true also. If the number is bigger than 1, then you should have a plus for the exponent. Okay, what about this 0.0000004 meters, writing in that in powers of 10 notation? I'm going to let you do that. So pause the video, do that on a piece of scratch paper, and when you're done, let the video play again. Welcome back, and I would do this by moving the decimal is my choice. So I have to move it once, twice, 3 times, 4 times, 5 times, 6 times, 7 times, and I'd get 4 times 10 to the minus 7. When I'm moving the decimal to the right, I'm making this representation out here a larger value. 4 is larger than 0.00004. So I must use a negative for the power of 10, 10 to the minus 7. When I move the decimal to the right and then record that number, I must have a negative for the power of 10. I moved 7 places, So we have 4 times 10 to the minus 7 meters. 4 times 10 to the minus 7 meters. And you should practice with this a little bit more, or ask your instructor. If you have questions, that's where I'm going to end this video. Another one coming up on multiplying and dividing these numbers. So again, you can catch these videos at astronomy.gpclements.com, astronomy.gpclements.com. And I'll probably throw a few of these in my physics website as well. But astronomy.gpclements.com. And for the physics videos, physics.gpclements.com. We'll see you later.